It's my great pleasure to be here. So actually, I have worked with the Howran more than 5 years, but never met him. So this is my first time to see him in person. So everything is changing. So also, for the first page of I'm all the mechanical engineering background. But when I was student, I decided to learn about this metamaterial in the PhD. So some of basic textbook is Professor Stefan Meyer's book. So I'm very humbled to present my work to be here. But anyway, I'm all mechanical background, so not much physics today. So basically some manufacturing. So first 10 minutes is about some brief overview. What's the metamaterial and how this metamaterial field is developed. And then next 20 to 30 minutes is the most recent progress in research. And last 10 to 15 minutes is about some remaining challenges. So what we need to do making this physics into the real technology. So before that, let me just introduce where I came from. From here is a Korean, South Korean map. And this is Incheon, so Melbourne to Incheon is a 12-hour flight. And we are locating here. So this is about 2.5-hour high-speed train. Actually, this is after Korean War, 1950. Just a small fishing town. There was nothing. But during the 1970 Korean industrialization, it became some of the industrial place, making the old iron, steel, for car manufacturing, heavy ship industry, and so on. So the company name is POSTECH, Pohang Steel Company. So this guy has a lot of money. So right now the revenue of this company is number 3 in Korea, next to Samsung Electronics and Hyundai Motors. But anyway, this guy, founder of this company, has a lot of money. So and he has some vision for the next thing is about education. So he traveled all around the world and visit many universities, Harvard, Stanford, and Cambridge, and so on. He found the model. Good model is California Institute of Technology. So we already have a Seoul National and KAIST. So he wants to make some unique model. So Caltech is very small. So we are follow this model. So undergraduate student every year 300, and faculty number is also 300. And so you can keep everything fully funded. So you can see the very small campus here. But I want to show this one, two things. Two accelerator is in here, only one in Korea. So synchrotron and this linear XFEL. So you can imagine how much money from single donor, donated to make a university. And this is some number. So this is about some small university. We are, only tech university. So less than 5,000. So considered a small university by this high Times Education. So we are next to Caltech last year, this year also number 2. And actually our department, mechanical, has a agreement for dual degree program with Monash Mechanical. So I hope we can send some students from next year maybe. So that's some introduction of our university. And let me start from some human history. So this is the materials development, materials discovery, and how we can manufacture them. So using stone, we can have easier hunting and making sharper tip and finger grip. And then we found this alloy, and then this iron, steel. And now we are living the age of silicon. So we found the silicon, and we know how to handle this one. So this, etching, lithography, doping, and we know this one. So this is base of the electronics age. And next to the silicon, we don't know yet, but this is a history. So maybe 30 years later, we can look back to history. Okay, that's the right material, change the world. So candidate is many, nanomaterial, quantum dot, graphene, many Nobel Prize, and I hope metamaterials could be one of them. And if you see some discipline, industrialization-wise, this is the first revolution, mechanical engineering. So we have an engine, so we have a very huge power. And this is electrical engineering, second revolution. Now we have a 24 hour. And this is electronic engineering. So right now we are living here. So next, again, we don't know yet. But many people talk about this AI. That may be true. But you know, many people ignore new revolution does not banish the previous revolution. So if you see the car, now electricity is in battery. Many semiconductor chip in the car. And you know, all the like photonic technology, camera, LiDAR, and so on, is being augmented reality driving, is being added to the car industry. So it's like a stacking of the technology. So I hope this photonics, optics can contribute to previous all the technology, electronics. So develop some overcome the limit of the electronics limit, semiconductor limit. So anyway, that's the reason we try to utilize this optical technology, very useful for our world. So this is one important slide about science to technology transition. This is the science, and this is the technology. So usually take like 50 years in history, and less than 5% is going here. And to do that, there should be some important event, breakthrough. So simply, if you imagine World War, atomic bomb is made like this way. So to win, the war, the completion of atomic bomb only take, 2 years, 3 years. If you saw the Oppenheimer movie, COVID also same here, right? And anyway, this is a microtechnology or electronics. We can tell they are very mature technology. So we have a lot of daily life benefit, but all the nano, metamaterial, maybe, that's not, we don't call the technology, we call science. So maybe the most of the work, even though I'm showing today, is most of here, development of the proof of concept. So whether clocking is doable or not, something is really doable, but scientifically makes sense, but they even didn't go to the technological level yet. Main reason, this is a bottom line, manufacturing, low cost, manufacturing, repeatability, economic region. So that's the basement. And then company think about, okay, can we get money from this technology, making some product? And normal people say, do we need that? And society think about, maybe we don't need this invisibility cloak in our life. So many complex reason, but bottom line is a manufacturing baseline. So that's the thing. And metamaterial is about, I think, 25 years about. So we are very important technological, this hill. So maybe next 5 years, if we show some manufacturability, feasibility, it may go here. Even though we show that it may not go there. But anyway, or without that, it will go, vanish like become hype. So this is some of the dream technology in my early age, my elementary school. And this is the one reason I jump into this field. But this all is about some extreme manipulation, control of the electromagnetic wave. And this thing is very interesting device here. It's Japanese animation. This device called Scouter. So if you wear this one, you will see holographic map in this device, where the enemy is coming from and who they are and so on. So this is a current version of AR glass. So 40 years ago, Japanese writer thought about this thing. It's very amazing. So I like to have this one in 1987. So this thing is being realized by some of the support, not 100%, but by some support of the metamaterial. And metamaterial people think about something, this is some in the dictionary, beyond the strange, something over thing. So if you Google Meta, now it's obviously Facebook will come out first, but this is one interesting tree, Meta sequoia. So sequoia tree exists first. In California, there is Sequoia National Park, but people, wood scientists found a new tree. So they look like sequoia, but genetically totally different. So which means they are different species. So they named this one like Meta sequoia. And some of you use to the normal people, like the metaverse is about virtual reality place or game, but we need a more scientific, some concrete definition. So this is what we are familiar about material science. So chemistry-based one, gold and quartz is different material because their basement atom is different, gold atom, silicon. And even though we have the same carbon atom, they're due to Bohr's condition, graphite, diamond, we're very familiar. But anyway, this is based on this all the chemistry-based material definition. But scientific definition of the metamaterial is artificially structured material and based on meta atom. So we have to define unit structure, atom first. And then there's some physical configuration, like a shape of the, some atom, like a gold is, bulk gold is like a shiny yellow noble metal, but like a 10 nanometer dot of the gold is like a blue color, violet color. So, and then we can place, and we have to observe some interesting electromagnetic wave property. So it started from optical frequency microwave, and now it's expanded to all the wave science, acoustic, elastic, even earthquake wave. And then what could be interesting? So this is a epsilon mu in EM. We distinguish some of the material here. And in dielectric, okay, let me go this one first. And this is nothing new, Snell's rho, rho index to high index. We know how to handle this one. And high index to low index, this is a critical angle. It's also we saw in the textbook. But metamaterial can do far more than that. So this is the demonstration of a refractive index of 10,000 in terahertz. So which means we can control the light 10,000 times more than that what we can do in the air. So this is dielectric case. And people show like ENZ, hyperbolic, mu NG, many different interesting properties we don't see in the nature. And also even found this area, double epsilon mu minus thing, and negative refractive index, and then perfect lens, super lens, invisibility cloaking. So many interesting phenomena can be observed. So people was fascinating, like me. Metamaterial is very interesting. But actually, metamaterial exists in the nature, very old history. So this is like Roman microscope you can see in British Museum, London. And this is like we saw the cup outside is a green color. The light is inside is a red color. So asymmetric transmission. So people didn't know why, but they know how to make them. So while they making this glass thing, and they put some powder. So this powder, and they could make such a color. And then later they realized if they make a fine powder, become violet, and coarse one is go to the red, and they make this rainbow color, making stained glass. And now we understand this is a plasmonic property of the metallic nanoparticle, so we can understand by equation. But anyway, it existed already 1,500 years ago. But why until 2000 was not become, people didn't realize this metamaterial in reality? My opinion is about this reason is about fabrication. So to work on this metamaterial in the visible wavelength, we have to control the shape, make the about 10 to 100 nanometer length scale, the fabrication, structuring. But nanofabrication tool was not famous until 2000 around. And after that, E-beam lithography, ion milling, self-assembly, all the nanoparticle synthesis was introduced and become popular. And then people could start investigate like a cloaking, perfect lens, and super resolution hologram, microscopy, and so on. So fabrication has been important to do that. And because this is one example, like some of early theories, like even 1968 from Vesel-Lago, Russian mathematician, he proposed like this negative index medium. But nobody didn't trust this result because people didn't see that. So they consider this is a mathematical trick, mathematically correct, but it's not true because we don't have this one in the nature. But until 2001, there's Professor David Smith in Duke actually showed that using this double split ring resonator, microwave actually can bend it into the negative refraction. So now people trust epsilon mu can be controllable by this structuring. And later, a few years later, using nanofab, my colleague Jason Valentine made this thin film multi-layer and drilling the hole using ion milling. And this is a negative refraction in IR. And then later, many things, visible terahertz, UV, with many different design, many different the fabrication methods. And anyway, here's the important thing is now people know actually the property of electromagnetic property can be really controllable by some of the structuring. So using some material, some shape, some placement actually happen. So invisibility cloak is similar. So a lot of drilled hole in the silicon 2D, we can control the light, the pathway. So this is like green is become hidden zone. Wherever light comes in, it couldn't arrive here. So making the invisibility cloak called carpet cloak. And later, the three-dimensional, very beauty of the fabrication. So 3D carpet cloak has been demonstrated. But the problem is, this guy is very hard to make it. So making this guys at the time like 30,000 US dollar. So, but this cloaked area is 100 square micrometer. So it's already very hard to see. So why do we need to hide this guy? And similar is very difficult to make. Repeatability is almost zero, I think. So I realized this scalability, even though we can make this one very large using drilling hole forever. So, but maybe we don't need it. So community also think about, okay, so invisibility cloak is some of our ideal place it can go, some scientific dream, but maybe we can do something practical, something beneficial to the community, beneficial to the industry. So this is some right side is some of optical technology, current optical technology can be integrated in many different disciplines. This is like classical optics, like objective, laser manufacturing, prism, and so on, like usually standalone optics. But these days, optics is going into the many different things, like electronic device, Face ID, the virtual reality device, and LiDAR, and so on. But baseline is they need some good function optically, like overcome diffraction limit and so on. At the same time, they need to be very light and very small, compact, to integrate it into the cell phone and virtual reality device and LiDAR and so on. So, but the problem is existing classical optics cannot solve those problems. Conventional, this is a refractive lens, refractive optics. So light comes in, based on Snell's law and based on the geometry, they can do this focusing, but bulky, but very old, long time. Industry is very well exist. And this Fresnel lens is making this one same function, but making little thinner. But you can see, although their phase information is translated to in the same height by this gear shape, but their performance is not as good as this guy. This is called diffractive optics. And making this one is not easy. This you can imagine the cutting of this glass is okay, but this is more complex. So people use the injection molding, making some mechanical engineering technology. So this is the beauty of the classical conventional refractive optics and diffractive optics. So this is like 9 combination of the plastic lens in your cell phone. So they have 20 million pixel, like 30 times zoom, but still they have some, they couldn't make it thinner due to their physical thickness of the lens. So we have a camera bump. And this is a diffractive optical element, diffractive optical waveguide and lens. And this is big, so heavy, because making the image projection, holographic image, and waveguide, and come back, so bend to the eye. So this is some minimized volumetric space. So this is we couldn't solve the problem of the very thin, no camera bump, and like AR glass, like a real human glass. So this is not what people want. So to overcome this limit, people study about, well, we can control like sub-wavelength features, sub-wavelength optical property. So using this nanostructure array, metamaterial, and do the same thing. For example, focusing, rather than using this geometrical, the refractive index, we make a lot of nanostructure, but they act as like this focusing function. So light comes in, each nanostructure interact with them and do something. Go here, and to do that, we need some phase information about quadratic phase encoding into their structure. So in 2D. And linear encoding, we can do steering. Like 0, we can making reflection, and so on. So what we need to do, making this, find the correct meta atom basement structure, and what material is it related to wavelengths usually, and then how we can placement, what is the unit cell and pitch, and how we can make them. So, and then let's experiment if this focusing function is coming out or not. And past 10 years, community has made a lot of effort to show, making the super resolution hologram, and this Howran is expert in orbital angular momentum for image, the degree of freedom increasement, and this lens making this objective making such a thinner, and LiDAR making bulk mechanical scanner into the optical finger-sized one, and so on and so on. So basically, optical function is given. We can replace everything in principle. So this is a simple design to application. Some flow chart. We find the atomic structure, and this is related to what we're going to control. So we're going to control amplitude or phase or both or polarization. It will determine what type of structure you're going to need. So for example, this rectangle is using geometrical phase called PB phase, and this rectangle structure is usually working. And these guys are like polarization independent because they are symmetric. And material like TiO2 is a good material for visible because high N, low K. And silicon is good in IR, also in high N, low K in the visible. But on the other hand, silicon is not good in the visible because high K. So that's some criteria how we choose the material. And fabrication, what type of thing we're going to use, e-beam lithography, nano imprinting, polymer-based direct laser writing, and so on. And then final application. It can be used as a lens, as a convex lens, concave lens, and holography, and so on. So in the year 2019, it is chosen from Davos Forum. It's also one of the emerging technology. So here is like a tiny lens will replace a bulky glass component. So this is one good example in our lab made. We purchased like an IR camera from manufacturer, $1,000. And then this is a convex lens, is integrated and take out. And we made the same lens like this way, but functionally same. But you can see this curvature is gone, flat. We call this one flat lens, and thickness become much, much thinner. But if you zoom in, there is a lot of silicon nanorod array. So they are doing all the light go to the one spot, making focusing. And further integrated into the this camera again, and functionally same. So even though camera is not dramatically decreased because all the electrical part, mechanical part, but optical part become smaller, thinner, and working same, actually the resolution become better. You can see some of chart cannot be resolved by manufacturer provided lens, but this meta lens can imaging this guy. So this is not super resolution scheme, but image contrast in this MTF optical chart become better. Main reason is the spherical aberration is gone because this is flat, so it can collect more light than this typical this spherical lens. So then why not to use it? Better function, smaller volume, and why not? The problem happened is in 2019. This lens fabrication cost was $5,000 US dollar. But I mentioned camera is $1,000, so we cannot use that. So no justification. But in the end of this talk, I will show this lens now become less than $20. So now we can use that, maybe. $20 maybe more still expensive, but we can use that now. So this is some of earlier demonstration in few years ago, and still like a one lens design. But we need to do 2 lens, 3 lens, complex like 9 lens, but this is not easy yet. But people are making effort in the community. And this is a simple demonstration is we can do like a zoom on and off and focusing in and out by some of integration with the liquid crystal, but very early stage is still, we have to admit. And this is another some example. We can also just change the convex lens into the one single flat lens. And we can do also some complex objective. This is a very expensive objective we can use in microscopy. Also a lot of biology people rely on this high numerical aperture, high resolution objective. But problem is expensive, and this length is very long. So this is some of the drawback of this guy. So why maybe should we try replace like one single objective, one complex objective into the one single lens. So we try this one. So it's worked well. This is like a dual wavelength metalens is for single molecular imaging. So excitation is a 635 nanometer collection, and then 670 nanometers. So dual wavelength. Actually, this is the shape of the metal lens arrays. You can see a lot of nanorod cylinder shape, and this is okay. So 635 and 670, they're focusing. Not the best, but okay, working. And this is some comparison chart. So this is much better than aspheric objective lens. For example, Na less than 0.5. This metal lens is much better in terms of a single function. But some of them is like we couldn't beat like Na 1.2, 0.09. Still this guy is better. But some of the charts like up to Na 0.5 maybe can be replaced by one single metal lens. So some of the comparison type achromatic lens, you can see this is no single molecular imaging. So this guy is not good at all. But metal lens can do single molecular imaging, but maybe a little lower than this guy. So here, so some of the thing. So still, we cannot replace everything. So some of very important, very expensive, achromatic objective lens is still worthwhile to use that. But maybe a few years later, we can combination of 2 metal lens to replace one very expensive some objective lens. So people is working on, including myself. And another good example is some important device. In my opinion, is this face recognition system, or people call short distance LiDAR. Using LiDAR light, we can make the 3D map or depth sensing. So if in your Apple phone, there is some Face ID system. So simply how it works, this is one device called diffractive optical element dot projector, and light comes in, pass through this device, 10,000 dots is being spread out. And then this IR camera is taking a picture, and they compare, analyze what it is. So compare with the original secured data, and then it's on and off. So go or stop. So this is simple face recognition system using IR camera. And there are actually few type of things to do that. Famous thing is like the time of a flight. It's used in car, long distance LiDAR. Measure the time, the laser go and back, and measure the time, so making the 3D depth map. And passive stereo is a simple human eye system. 2 eye, 2 camera is taking a picture. The brain is calculating the distance, so recognize some of object. And structured light is like a Face ID. So 1 camera and projector is providing some of light information, collecting, analyze. And combination of these 2 is called active stereo. So 2 eye and 1 projection system, so getting better than this guy. So if you think about some human vision system, so if you in the cave, you don't have much light information. So you will likely make a mistake. so you don't have some right guess. And if you close one eye also, you will likely make some mistake. So the important thing, two correct eye, two good camera, and enough information of light. So that's the important thing. So basically this project is providing more light. So whether they trying to making some of the case and camera is very easier to detect them. But problem of this diffractive optical element in current Face ID, so using diffractive optics, so they have a field of view limitation around some angle of 100 degree and size issue about centimeter scale. And yeah, that's the thing. So why do we replace this one by metasurface? So samely, what we did in the lens, we can do same thing. 10,000 dot array, but better field of view, 180. So like no angle dependency, so 180 degree, and size become 10 times smaller than Face ID. So again, so we have a little benefit, but more benefit, I think the field of view issue, diffractive optical element cannot do that. So this is some conceptual view, 180 degree beam propagation. And simple design is like we make using some called supercell method. So this is like atom go to the molecule. So one set of this molecule consists of many different atoms, and one molecule acts as a single standalone device. And light comes in, all the molecule pass through the light, and interference between the cell, making many of the interference. So that become about 10,000 dot array in eventual far field. So this is and then take a camera and simple extraction algorithm, we can calculate the distance. So that's how we can draw the 3D map using this active stereo device, stereo camera. So this is made by silicon, and you can see the dot array in red, green, and this is actually line array, not dot. So we can shape any type of structured light. So dot, line, triangle, rectangle, whatever. So depend on your intent. And then we further, this is made by lithography, and further we try to making this one by nano imprinting. So benefit of the nano imprinting is we can do in curved surface, flexible substrate, and cheaper than lithography. So using this polymer resin, I'll talk to detail later more. So nano imprinted glass shining laser and dot array. So anyway, conceptually also happy to realize this structured light in 180 degree. But problem happened in the later. So then, but efficiency or the performance is not as good as our best expectation. So reason is here. So we have a random dot array here, but we don't know this is a correct pattern for 3D depth sensing. We don't know. So we can try like a line array, periodic dot, like a rectangle. So, but we cannot try like a 10,000 thing. So we cannot do that. So we can compare maybe 4. Which one is better? This is still better. So what we did next time, rather than doing heuristic, like a trial and error based design, what would be the best pattern for the 3D depth sensing using this metasurface? So we cannot do that. So we need to rely on this AI, deep learning. So this is actual AI generated the structured light pattern. This is very continuous, like some wave, some of a river shape, and this is the best for our depth sensing. And this is suggested like some structure of the metasurface, but similar. But we constraint making, we're gonna use the rectangle anyway. So we don't need a very freeform shape, very complex shape. We cannot do that. So while we are keeping the rectangle, what is the best pattern? So this we call like so we do deep learning. So we call learn the metasurface. It generates some better structured pattern. So this is a deep learning cycle. So this is a phase map to generate what type of pattern. So here is the first, and this is a beam generation. And then generated beam is captured by camera. This is a stereo camera. And from there, rendered image is go to the depth reconstruction. So this is a typical cycle. And device is here. Following this the phase map, we will make some device here. But this is like a loop cycle. So compare this estimated depth into the like some pre-learned one or ground truth. And while this network is going on, they suggest a better pattern for better accurate depth reconstruction. So while this step is going, it's very quick, take a few minutes, and this estimated depth is going to the ground truth. And yeah, this is simple measurement system. So this is metasurface. And here another some improvement is the previous one is 180 degree. So only the front side measurement. But now light comes in 180 degree into the front side, and half is come back to the reflection. So another back side is getting imaged together. So now it's 360 degree 4 pi imaging is doable. And now so we have a 4 camera, and fisheye camera is used to detect this 180 degree field of view. So anyway, this is simple system. So even though beam projector is miniaturized, still bulky. Fisheye camera is still bulky. So some of our colleagues like JJ Hu in MIT, they are working on miniaturize this fisheye camera itself. So very high field of view collection camera. But anyway, so this is some one scene and 1 and 2. So this is the pattern. From pattern, this is the depth reconstructed map, and okay, well, works well. And even dynamic imaging, so movable stuff. This was static, but dynamic imaging is very quickly getting followed, but not real time. It's about semi-real time. Take 1 minute. So if you change the direction. So, but if you wear the AR glass in the future, if you change your head direction, and new information should be collected from what you're seeing. So this will be important to be very quick and accurate depth information. So compare, this is the current result, and this is our previous method. So 5 times better accuracy. And this is just a passive stereo, just the 2 camera, and 20 times better accuracy. So we will benefit even our previous method and very conventional technology. So maybe useful in the future. So working on improve some device performance and some this learning time cycle decreasing. So many following work is ongoing. And another recent example what we did, this is like AR glass, very high tech. So I also rely on, metamaterial is a very high tech science. It has to go like, very fancy electronic device, computer, and so on. But actually, very low tech, agricultural science, like, dairy thing, it may contribute using this nano optics. So I didn't realize that. But recent collaboration with the New Zealand government, what we did, this is like a nanostructure, high index dielectric, titanium oxide. If we make a sum of a structure, it's well known, we can control the reflection and absorption. So we can make a color, what the gold nanoparticle did in the history. And then this is called structural color. So people make E-beam lithography making structure, and we can do nano imprinting. So we thought about, we may directly pattern this one into the apple or something, live stuff. Why not? So we tried this one. And then actually this apple can have some image formation called barcode or QR code, and they deliver some information. So what many people do using this QR code scan, and this manufacturer and production date, and this is a very simple thing we can do. And some of the hidden images using this some structural color, and sometimes we added some hologram function here. But here more benefit is this is a water soluble. So we mixed this nanoparticle into the water soluble polymer. It's a non-toxic, and we can wash this water before eating, and this become edible. So all the TiO2 is gone. And you can do in the plastic packaging, Usually we use the sticker, right? But you have some hidden QR code here, the price, whatever, some production date, and later you just throw away after some water washing and no waste anymore. So nano optics can meet some of polymer science and prevent counterfeiting and some of the waste in labeling. So we call this smart labeling. It demonstrates some very exaggerated pattern on the apple going to water, it's gone. So something interesting. So I'm trying to thinking what maybe we can do some for shipping or some long time shipping from like ocean that take a very long time. Even it can measure some humidity, so we can maybe use as a sensor. So still again, some following works is ongoing, but some change our direction to agriculture or wood, animal, and many things can be integrated. So we have to discuss with many colleagues, even in different fields. So that's some benefit we had recently. So structural color is a very simple physics. Nothing, some of reflection control, some of fabric petal cavity. But this is in our earlier work using aluminum plasmonic material for generation of the reflection color. But you can see the color map is very small, not good color. And later, gold is more famous to making more color, but we added more complex shape into the gold, this chirality addition. It make a much more broad color range. So I was very happy. But problem happened for the application. Even though their color map is pretty wide, sRGB, Adobe RGB, but this color from plasmonics is human emotion is not being satisfied because their hue saturation value is not enough. This intrinsic loss of the plasmonics in the visible metallic nano particle. So I was a little frustrated. We cannot use this beautiful color into the real display technology. So people now trying to use some dielectric, so less loss in visible. So the silicon, like gallium nitride, also they can make a color. But rather than plasmonic resonance, here the Mi resonance is being used. But anyway, the good thing is we can control the color. We can make the color. So this is a simple light green and dark green from silicon nanorod, and red, also blue is a doable, and color map pretty expanded, and hue saturation value is good. So human can feel this is a good color. And this is some of the earlier demonstration, simple green color only, few humble images, and later getting better. We use the engineered silicon. So this is a normal silicon, but we added some hydrogen to suppress the K value. So this gets a little more better color, but still not the best. And finally, we make some very high resolution, 100,000 dpi. So you can see the almost photorealistic color. So human cannot recognize this is a silicon. This is just a picture, photo. So anyway, 100,000 dpi is the maximum human can recognize. So in terms of resolution, maybe enough now, using this nanostructure. But only the next thing is remaining is how we can integrate this pixel into the display technology. Display use liquid crystal for LCD display or OLED, some integration. That will be next step. So it's not easy to do in university. So industrial effort should be a company. But you can see like red, green, blue, CMY, black and white, and many combination based on this cell as now full color can be achieved by the silicon nanostructured array. And many other material can do, gallium nitride and silicon nitride, and so on. So this is about some control of the amplitude of light, so called structural color. So a few minutes, I'll talk about very briefly about hologram. Hologram is a control of the phase information of the light. So this is famous work from Thomas Jangraf in Germany. They use a gold nanorod and change the angle. This rotation angle is related to geometrical phase control. So theta change of making two theta phase different. But anyway, you shine the light here, circular apply the light, you will see like a very high resolution. That's Einstein image here. But at the time, you can see this is a very dark room condition. Their efficiency is very low because of using gold. But physics is given discovered here. And now what our role is very simple, engineering. How we can increase the efficiency, what is the best fabrication, and some application, and so on. So what we did immediately, green color, and using polysilicon, easier fab, and transmission type. So efficiency increased to 7%. So okay, better, 7 times better, but still not enough. And then we use like a double, dual wavelength, green by silicon, IR by this golden nanorod array, combination independently work. And why not UV? Silicon nitride and silicon, so dual wavelengths again, UV and visible. And this is two color, aberration corrected one. So now the unit cell become little more complex. While the rotation happen, their thickness, the size also changes. So a little more complex, two color combination. But 3 color we fail. This is too difficult. So analytic solution is not coming out, and this optimization doesn't work because we fail to generate the 3 color by using this method. So, but we didn't give up. AI, deep learning, so helped us, and they simply suggested a very good design, making RGB, achromatic hologram. Even they suggest the material and showing the very high efficiency. So one device, now we can generate like a 3 hologram image with the 3 full color. And this is another example. AI supported us 18 degree of freedom for one device. And this is like a different depth. So we can generate like a 3D reconstructed holography, even though resolution is not very high enough yet. And wavelength multiplexing, also very important and not easy. And different wavelengths, but one device, different wavelength, different color, different image. So 10 degree of freedom is achieved. And this is not just achromatic, but beautiful white band color. But here I want to show is we achieve like 90% of the almost the maximum conversion efficiency using the packed TiO2. So you can see very bright image hologram. So Einstein is like 1%, so it's a very dark room condition. Okay, maybe in VR. But if you wear the AR glass, you are facing sunlight or room light, so you need a very high contrast image. So now we achieve a very high efficiency from 1% to 91% took like 5 years. So very technological development is even very fast in this academia. So now this is a combination of the amplitude control and phase combination, very simple engineering. So these two devices is the same in terms of a hologram because their rotation angle of the unit cell are same. So geometrical phases control is the same, so you can see the same hologram here. But in your eye color is this is a fatter, so red one, the thinner green color. So combine, keeping the angle same, and you will see the same hologram. But the fatter one is become like a red, and thinner is a green background, so you have a different image. So we can control amplitude and phase simultaneously. Not 100% independent, but we can control somehow. And further is applied to some of our some engineering application, humidity sensing and some image encryption. So we changed this silicon by this polymer called the PBA hydrogel. And hydrogel is absorbing water and become fatter. And while this humidity comes in, getting fatter, and they are stuck together, so it's like screwed up. So beginning, they have a hologram image because their shape is correct, but humidity in, and their shape become ugly, and no more hologram. So it's structurally broken. And while they are broken, some time, some amplitude, some structural color image suddenly happen. So this is your password and gone. So we claim this is one-time password or one-time security sticker. So that's our named this work, and we can do further. So bottom and top we stand with the metal, and they don't collapse. They can swell, but they come back to the original shape. So hologram, no color, humidity in, hologram is gone, color is come out, humidity is removed, and hologram come back again. So this is a reconfigurable, configurable some security tag we claim, humidity sensing. So, but the problem, okay, so all the beautiful work about all fabrication is a very small area because mostly using e-beam lithography. So they are not good for mass manufacturing, prototype, expensive, and repeatability is bad. So what we need is some of mass production, reliable, repeatable, and high yield, and so on. So indeed, this Davos forum commented about, okay, this is good technology, but expenses are very high. Difficult to precisely place a nanoscale element on centimeter scale. So that was 5 years ago. But we can do now centimeter scale, even larger. So what we do in our current center in Korea, we develop some manufacturing method and what is the related good material, high index, low K, and what is good for CVD, what is good for imprinting, what is good for etching, and so on. And eventually, this will become more important, design, because in 1 centimeter metal lens, there is a 1 billion number of atoms. So we cannot do full simulation optically due to computational power. So how we can develop some good design very quickly? One lens design takes 3 weeks this time, but we have to minimize like 1 day, few hours. And we have to develop some faster software and deep learning and database driven. So many design efforts will be needed in the future. But I'll talk to 2 simple things about material and manufacturing. So this is our material development in the community, plasmonics. And then we use dielectric, high and low K. But this ALD, MOCVD, is a beautiful material, but extremely difficult to do that. 1 micrometer ALD is painful, so not scalable. So what we need to do, functionally similar, but can you make a cheaper spin coating or CVD? And then we don't need to use TiO2 gallium nitride. So industry doesn't want to use that. So that's our approach. So simple 1 slide. This is a typical CVD silicon, high end, but very high K in the visible. So in opaque in the visible. But this is a red line is a new silicon, engineered silicon, little low end, but still comparable to TiO2 gallium nitride. And K is quite compressed to almost 0. So now, which means it is transparent in the visible. And then we can use in silicon control RGB now, full control of the visible wavelengths. And this is some baseline and CVD, cheaper. And this is further expanded to IR. Obviously, silicon is good in IR. And further UV, nitrogen doping. So visible is a hydrogen doping. And so this is one CVD material and deposit and exposure and etching. So this is a typical process what you do. And what we develop another thing is a nano imprintable, very high index of polymer. So usually nano imprinting is using polymer, but polymer has 1.5 refractive index, so not good for phase control enough. But we added the functional nanoparticle inside, so index go to the 2.5, 2.2, and then they can work as correctly as the same as similar as a TiO2. So this is some of the candidate silicon nanoparticle embedded resin in IR, zirconium oxide in UV, dim UV, TiO2 nanoparticle is invisible. So we can assume this guy is just a TiO2, silicon, zirconium oxide is a thin layer. So that's one thing, but imprintable. And last few slides is about now patterning. So it's a combination of the e-beam lithography. This is obviously we cannot avoid that. because nanoscale pattern. So we make this E-beam original pattern as large as possible. And then usually this is the last step. We experiment and that's it to publish a paper. But now this pattern, original pattern, is translated to the mask of the photolithography. Photolithography is a mass manufacturing tool. So we can do stepping, many repetition, making in same device, repeat of the same device into the 8-inch, 12-inch wafer. You can stop here. So semiconductor industry stop here, dicing, and this is your 600 metal lens. But we can do further using this one as a master mold. We can do another nano imprinting into the flexible substrate, transparent substrate. So this is the E-beam step, typical, but getting faster, technology developed. And this is a photo mask for photolithography. And this will be metasurface now, 4 centimeter one. And then the projection. And then this will happen like that one. So array of the 600 metal lens array onto the 12-inch wafer. So you can stop here. And I mentioned you can combine with the nano imprinting technology. So this is, I will skip due to the time. So this is finally imprinted, replicated pattern. So as long as your master mold is not broken, you can do forever. But usually some degradation happen although. So anyway, this is the thing. And lens performance, you can see, very close to the ideal, the MTF chart. So we are very happy. But aberration is not corrected yet. So you can see some achromatic image still, but work in comparable to this VR system. So we have a good image, although we have some edges and blur due to the aberration and some imperfection of the device. And AR is much difficult, but we are working on. And computationally trying to correct this aberration because device-wise it's very hard to making visible achromatic lens at this moment, while many guys are working on their own design and their own methodology, but efficiency issue, size issue. So at the intermediate some method, we are relying on some computational support to correct the aberration here. So this is the ground truth metal lens imaging. Single wavelength is okay, but this is visible. You can see little blur. But this is a constructed one, some corrected image is much better than this metal lens one. So, but computationally it's not heavy, so it should be okay. And last one, we are imprinting lithography, but this is another mass scalable thing, roll to printing. But only the drawback is we have to use this plastic film only. So you can see the metal lens array is continuously fabricated in this plastic film. So another scalable thing we are developing. So it's done. So important thing is to surface metamaterial, go to the real technology, manufacturing, material, design, all have to show the scalability. This is real manufacturing, but we are focusing more on this material side and patterning side, but many experts working on this clever design and so on. So our immediate application is about sensing, LiDAR, face recognition, and AR/VR optical component system, including waveguide. But in like 10 years, 15 years later, many different this meta surface optics technology will be our in the real world. And thank you to our older student, and thank you for time you guys be here. Thank you very much.
Thank you, Rob.
Excellent. Quick question, Junsuk. For the color generation, how do you make black?
Black is some the RGB. We can combine this three color combination. It's addition is doable. Also subtraction is doable. So black color, white color, both can be generated. But actually the polarizer in this basement, two polarizer is helping adapted from LCD, liquid crystal display technology. So.
very nice talk. When you've compared the quality of a lens, you had three curves. One of them to the usual lens, one meta lens, and so some theoretical maximal value.
Yeah.
Could you provide more details what bounds performance of a lens from theoretical perspective?
Okay. So this is the calculated diffraction limited length, or theoretical limit. And so why this line go to here is considered better lens. So here I only compare like a manufacturer's provided one and our lens. So still you can see very far from the ideal performance. So in this lens we didn't optimize the thing. So we don't know. It may go to here. It may not go to here. The reason here, this lens here is made by not highest quality of silicon. This is the silicon embedded polymer resin. So refractive index and this K value is not as good as the silicon I mentioned in the later. So if we do this one just a normal silicon, CVD silicon, and it will go to much closer here. So I think it's around 90% of the area size. So which not 100%, but we may use that. And what we optimized for best is the last slide, this one. This one. So this is based on TiO2. So TiO2, this green line is a TiO2 ALD material. And this orange line is I didn't explain, but this system, TiO2 coated resin. So different material, but TiO2 is not fully filled inside, but only outside of TiO2. Inside is a polymer, the column. So that shows the same performance of the almost ideal value. So which means only the light is interacting in the thin shell. They don't go into the polymer. So that's some little difficult mechanism we understand. But anyway, this is something we can make best in this lens. But if we change like a numerical aperture, focal length, it may be changed again. So then we have to optimize with some of the computational effort. So that's the reason I mentioned in the computational optimization is very important. Quicker and more economic, low computational power design will be important.
Thank you.